Exercise 7. In this exercise, we take a look at the functionality for computer-aided engineering inside Inventor. We'll begin by creating this part, which is basically a bottle opener. And we'll first design the part, and then we'll go ahead and apply a material type, and then we'll apply loads, a force load in this case, and also a fixed face where basically the top of the bottle opener will be fixed upon the lid of the cap of the bottle. So let's begin. Here you can see the finished product, as well as you have the ability to animate and see the flexion of the actual part. And this helps us identify also the weak parts, or the weak areas of the part as well. So this is called finite element analysis. Okay, so we begin with a new part file, standard iPart. We'll start by creating a sketch on the front plane, and we'll draw out, using these dimensions that we see here, the actual model. So I begin by taking the line tool, and at the origin, click and drag up a line, and this will be a 1/2 inch, so 0.5. Zoom out a little bit, drag out another line horizontal, which will be 2 inches long. And we'll zoom out a little bit. Then drag down a line here and connect it, and this will be a 1/2 inch. And then another line, very short little one here, which we're not going to dimension. Then click and add a line here at a slight angle. Drag off another line across, and then one here, just like you see. Now this one will be 0.2 across. And then we'll draw an angled line. Don't lock it in parallel to the geometry just yet. And this is going to be a 45-degree angle, and the length won't be defined just yet. And then draw this across, then another 45-degree angle down, connect it, and close. Hit escape, and now go to the dimension tool and add the last of the dimensions. So 0.5, and over here we're going to go ahead and dimension between this corner and this line here will be 0.5 as well. We could add the angled lines in. This will be from here to here, 45, and from here to here, 45. Okay, and then we could also dimension this from this line to this line will be 0.25. And you can see it's slowly getting constrained. I'm going to hit escape here and move some of these dimensions out so it looks a little bit better. Okay, now this, I'm going to go ahead and delete this line and put in a tangent arc instead. So I'll find tangent arc and connect from here to here. And then just go to the tangent relationship and add it between this line and the arc. And now we could locate that according to the dimensions given. So it's going to be from the center point to this edge. It'll be 0.35. The angle will be 25 degrees between here and here. The center point will be located at the bottom edge, 0.25. And then we just need to get this line collinear to either this edge or the one over here. It's like collinear. Okay, we need to put a radius. So go to dimension, put a radius on this. That'll be 0.125. And now we're fully constrained. We can then go to the extrude under 3D model, extrude boss, And we'll actually extrude this in two directions. So if we bring this up here, we select symmetric extrusion, and it's going to be 0.4. Now we could go to the fillet tool and add 0.3 radiuses on it. So on these major edges, click and select those. Apply, and then if you hit apply, you could type in the next value, which will be 0.1, and that will be all these edges. Wrap around. We'll put one around this edge of 0.05. In that case, it's not fitting on there, actually. We'll just leave that alone for right now. Alright, there is actually a hole that goes in here too. We could start a sketch on this face and draw a circle. And this is where the key ring would go. And you can find the center there. And then dimension that. The diameter will be 0.125. Now go to 3D model, extrude, select the profile, reverse it so it cuts into the part, and through all. Turn on the edges so it's a little bit easier to see. Okay, now from here we could go ahead and save the part, and I'll call it E7. Now what we want to do is we want to begin to run some analysis on it to see if it will break. So let's scroll down here in manual, and we could continue on. So first of all, we're going to go to stress analysis, create simulation. So that's under environments, stress analysis, create simulation. And in this case, we could just leave the settings as is. We'll go with the default on all these and hit OK. Now we're going to go ahead and first select fixed. And for the fixed location, imagine that right here is the top. Here, this face is going to contact the top of the bottle cap. Technically that's not going to move. That's almost like it's being pushed down and fixed on there. So we'll select that face as the fixed face. And then select apply and cancel or OK. Now select force. Now for the force, we're going to put in this case, technically the max force would probably be more like around 10 pounds. The book we have down 40 pounds just so you can see how much it's going to break or rupture. But in this case, we'll go ahead and we'll put in 40 as well. And imagine your finger being underneath here pushing. Your thumb would probably be up here somewhere. So the force would be coming up from the bottom. And hit OK. Now with that selected, we just hit simulate. In this case, the simulation tool actually prompts us and lets us know what's wrong. And we neglected to select the material as I had spoke of earlier. So for the material selection, we could go up here. There's a couple places you could select the material. We could go up to the top here, and we could select what material we'd like to use. In this case, let's go with ABS plastic. And now let's try and run the simulation. Okay, now in this case says the deformation is large compared to the model size. Please verify the load constraint settings. We added 40 pounds, which as I said is almost 4 times the amount we really need to apply to this. But it actually gives us the nice deformed shape that we're looking at here. So we could always change that and lower it. Now with the von Mises stress, the KSI, it's basically showing us where the areas where it could break. And there's different settings for KSI. It's something that we could discuss in class further. But basically, for right now, we're looking at the area where typically we might start seeing some location where it might break. The red being the highest KSI. This material, on average, ABS plastic, actually has about 180 KSI before we see complete rupture or breakage. So what we're primarily seeing here is it's bending, most likely, and maybe not, and maybe bending in such a way that it's not going to bend back. However, it's not actually going to rupture because it's not anywhere near 180 just yet. Typically that information is found on material data sheets that you could locate online. So for example, ABS plastic, one of the manufacturers is Bayer. That's the same manufacturer as Bayer aspirin, actually. And you could look that up and look up material specifications for the ABS plastic. And there's various types of ABS as well where they mix other materials with it. But you can find out the average strength, or tensile strength for that as well. And one other thing, if you wanted to animate this, you could click on Animate, hit play, and here you could see the actual animation taking place of it bending. There's also tools in here, adjust it. What you're seeing is an adjusted view of this. So if we go to actual deformation, we can actually see how much it technically would probably bend, which is significant. The other method where we're seeing times 1 is actually just reduced a little bit. And that completes exercise 7.